Welcome back to Engineering Physics PH8151 Arrear coaching series. And today we are going to see another question on unit number 1. So write a note on stress strain diagram. Let us quickly recall what is stress. Stress is defined as, so it is stress is equal to deforming force applied per unit area. So it is force per unit area. So strain, that is equal to change in length by initial length. What does it mean actually? Suppose if we are considering a wire, right? Let us zoom it out so that it is essentially a cylindrical wire. Now this stress is defined as the deforming force per unit area. Force is applied on this surface, so that this deforming force applied per unit area, which is normal to the surface of the wire, so that is stress, which is equal to force per unit area. And because of this application of stress, this material tend to extend or elongate to an length delta L. So you can define this length is L. Now we can define strain, that is equal to this change in length divided by this initial length, that is strain. Now we are clear about what is stress and what is strain. What we are going to do now, we are going to plot a diagram between this strain on this axis, that is on x-axis, and stress on y-axis. And we are going to discuss different segments of this graph. So this graph will look something like this, and we are going to see the different segment of this graph. Let us draw this stress strain diagram, x-axis and this is y-axis. In x-axis I have plotted strain, and in y-axis we take stress. Now this graph will look like this. Okay, and it has 5 segments. This is A, and this is B, and this is C, and this is D, and this point is E. So let's say this is segment 1, and this is segment 2, and this is segment 3, and this is segment 4, and this is segment 5. So now what are all these segments represents and how to interpret them? Now carefully look into this stress and strain diagram. This is the stress and strain diagram for a wire. It is the stress and strain diagram for an elastic wire. Now from the point origin to point A. So up to point A, if stress is increased, strain is also increased. Stress and strain has one-to-one relation. That is, if a stress is increased by the unit 1, then strain is also increased by the unit 1. So both stress and strain is proportional. So in the segment 1 up to point A, stress is proportional to strain. So if you look at this line is tangent line, so that this point A is said to be proportional limit or limit of proportionality. Okay, so this point A is said to be proportional limit. Okay, and now apart from point A to point B, this curve is no longer linear. So for the small amount of applied stress, there is an rapid increase in strain. Now in the segment 2, in this region between A to B, between the points A to B, stress and strain are non-linear. Okay, but from this point to this point, if you remove this deforming force applied, that is, if you withdraw the stress, then what happened? The material, the wire that we have considered earlier, will go back to its original shape. So that up to point B, this material will hold this elastic property. So that this point B is said to be elastic limit. So between point A to point B, the material has its elastic limit, which means if you remove the force applied, the material will go back to its original shape. Now segment 3. You consider the segment 3. This is a small segment between the point B to C. What happens is, even a small change will increase the strain little higher, right? Now in this region, what happens? If you remove the deforming force, the material will not completely go back to its original shape. Rather, it will possess some amount of strain in it, which means there is a residual of strain which will present in this segment, that is the segment 3. Okay, so that is called, this residual strain is called yield point. Okay, so this point C, let me write here, it is yield point. Okay, so this is the region, the point B, this is the region, end of the point B is the region where plastic limit starts. So one can say, in this limit till point B, it is elastic region. So if you remove the force, it will go back to its original shape. From B to the remaining portion is from this to E, the entire region is plastic, where I have to write I can write here, it is plastic region, where from this point to it goes like this from the end. This is plastic region. And point C is yield point. So this is, here there exists a residual strain and the point C is called yield point. And now segment 4, point C to D. In this region, for the applied stress, there exists a dramatic change in the strain, right? And if you remove the stress, the material will not go back to its original shape and it undergoes a plastic deformation. So this region C to D is plastic region, and the point D. So this is the point, right, where this material has a maximum deformation. Right? What actually happens if we consider the wire and if you apply force on it, what happens when it elongates? The wire thickness will decrease. Okay? So this thickness of the wire will decrease when you increase the stress. So in that case, at point D is the point where the minimum thickness of the wire is experienced. So this is the this point D is called, that is between C to D. So point D is called point D is called tensile strength. What is tensile strength? That is the maximum amount of force this wire can hold, provided it has the very lowest thickness. Okay, and segment 5, now at point E. Okay, and this is breaking stress. So when the stress is reached at the point E, then even if you withdraw the deforming force, this material will neither be in plastic nor be in elastic region, right? This will eventually goes down and the material is thinned and thinned and it eventually breaks down. So the material will automatically breaks down at the point E, right? So point E is called breaking point or breaking stress. So that this stress and strain diagram has 5 segments. First segment is called proportional limit. So from 0 to A, this graph has strain and stress has proportional relationship, and the point A to B, there is a nonlinear relation exists. So up to point B, this graph is called elastic region. From point B to C, there exists a residual strain, and where this plastic region starts and it attain its maximum at point D, which is called tensile strength, and eventually this wire breaks down at point E. So these are the major components of this stress and strain diagram, and these points that we have given here should be present in your answer script. This is the segment 1. And what is the segment 2 of this question? What are the factors affecting elasticity? Okay, so what are the factors that will affect elasticity? There are majorly three factors will affect. What are they? One is hammering, rolling, and annealing. Second, addition of impurities. Third one, increase in temperature. Let us see one by one how it affects. First thing, hammering and rolling. Hammering and rolling. What happens? So if you hammer the material, if you consider a material and if you hammer it, or you can roll it, what happens? Here the material assumed to be of crystal of large size, of uniform orientation in a large extent, it breaks into small or tiny crystals. Okay, as these are broken into tiny crystals, the elasticity increases. So during this process of rolling and hammering, elasticity increases. This is 1A. And 1B, what happens during annealing? First, what do you mean by annealing? Annealing is the process where the material will be gradually heated to obtain a particular temperature. After that, it will be gradually cooled. So that gradual increase and decrease of temperature, that is annealing. What it will do? It will form the tiny crystals, that is this constituent of material which are tiny crystals in initial stage, and because of this gradual increase and decrease of temperature, it transforms to large single crystal. This happened by the orientation of crystals in an unison, in an unidirection. In that case, elasticity decreases. So elasticity decreases. What happens to point number 2? Impurity. Okay, this we will understand by an example. Let us consider pure gold. It is brittle in nature. It can be brittle in nature so that we cannot use it for any purpose of creating or designing ornaments like chain or bracelet, ring, etc. But if you add some impurities, then it becomes ductile and malleable so that we can design ornaments. So that impurities will increase the elasticity so that it increase elasticity. Example, carbon and potassium impurities are added to molten iron and gold respectively. This is the case for addition of impurity. And what happens if you increase or decrease the temperature? So effect of increase in temperature, or you can also increase or decrease in temperature. So what the effect of temperature? If you increase the temperature, elasticity decreases. So that T increases, elasticity decreases, and vice versa. If the T decreases, elasticity increases. But this is not universal to all materials. Suppose if we consider inward steel, in some cases, if we consider inward steel, no change on temperature. The elastic property of the inward steel will not change, so that there are some exceptions too. Okay, so and these are the effect of different factors on the elasticity that we have considered: hammering, rolling and annealing, addition of impurities, and the role of temperature. So in the nutshell, hammering and rolling will increase the elasticity while annealing will decrease the elasticity. Addition of impurities will increase the elasticity. An increase in temperature will decrease the elasticity. Decrease in temperature will increase the elasticity. But it has some exceptions. Example, inward steel, it has no change on the elasticity when you increase the temperature. So in this lecture, we have discussed the different segments of stress strain diagram in first question, and in the second question we have discussed the various factors that will affect the elasticity. Thank you.